Like, let's say you have a massive PAM data set and you're interested in the frogs there. Now, there's no good model out there that's trained on frogs yet, but then you have a small data set of frogs, you annotate that, you do linear classification, then you have a linear classifier that knows to now distinguish frogs, and so that now allows you to use this big pre-trained model with a small linear classifier that you built on top of it, import that into ACODET, and then you can get species generation for your frog data set, even though you never had to like completely train a model from ground truth. And that is the power of these pre-trained models, and that maybe should come in the beginning of the video. Hi there, I'm Vincent. I'm a PhD researcher in the field of computational bioacoustics. So we're trying to develop machine learning models to detect species, or in generally help us with the massive amounts of recordings and trying to find what species are vocalizing, and trying to find out what machine learning models are better or worse for these kind of tasks. And I created a tool called bacpipe, which stands for the bioacoustic collection pipeline. And this is a tutorial video where I'm going to demonstrate how to use it and what you can use it for. And this is going to be quite a long video. I'm going to try to divide it into sections to make it easier for you to jump through the parts that are important. I'm going to really start from scratch, so if you have coding experience, then some of this stuff might be redundant, then yeah, feel free to just jump to the later sections. But if you are not that familiar with Python coding, then hopefully this will help you get set up and use the tools and yeah, benefit from them. So what we can see here is the main GitHub page of bacpipe. And so this is where currently I'm filming this, and we're just on version 1.1.1, which I just released. And so that's bacpipe here. We have we're having audio data that's coming in, and then we can modify some settings, and bacpipe gives us embeddings, classifications, and clusters. And the idea is really that, like, if you have massive PAM datasets, passive acoustic monitoring datasets, that don't have any annotations, and you're struggling to find the time to maybe go through them, then the idea is that there are quite a lot of machine learning models that have been developed in the recent years, and some of them are like trained on a load of data, and so they are actually quite capable of differentiating between characteristics in these sounds and also in soundscapes. And so while this won't give you a perfect list of all the species that are present, and especially not of the species that are absent, so it's like you still have to take it with a grain of salt when it comes to inferring ecological conclusions from it, it can help you really kind of like divide that data set up, maybe seeing patterns of high activity, low activity, and yeah, just kind of like maybe taking that first initial step of annotating that data a little bit further. And so so that's pretty much the idea, right? You put in either labeled or unlabeled data, but it's more intended for unlabeled data, and then you modify the settings, and it gives you all of these things. And so it is packaged, meaning that you can simply do pip install bacpipe, and then you'll have the package in your on your environment, and then you can just import bacpipe. And if you just run bacpipe.play, it will actually run like a little mini analysis. So why don't we go ahead and first of all download the whole thing. So we're not going to work with the packaged version, we're going to work with the repository, and then I'm going to make a video later on where I'm going to show how you can use bacpipe in another environment, in another repository that I created called ACODET for acoustic detection. And so in that we'll use the packaged version. But yeah, so for now we're gonna work with GitHub. So we want to clone this repository. So we go on code, and then we copy that. And I created an empty folder here. I'm doing all of this on Windows, by the way, just because Windows is like the go-to for, I think, a lot of yeah, bioacoustics people that maybe have their work computers. And so it also runs on Linux and Mac, as far as I know. Mac I haven't tested yet, but definitely on Linux. It's a lot more stable on Linux, and you have GPU acceleration, all of that. but to make sure that this is helpful to as many as possible, and we're going to do this on Windows. So I'm going to assume that you have Git Bash and Python 3.11 installed. There are a lot of other resources to find that, and so if you do have that installed, then you can just right click in that folder and you can do open Git Bash here, and that'll then give you this little window. And so now we can clone the repository. So for that we're going to do git clone. Okay, and now we're cloning the repository. Yeah, I'm not gonna put much effort into editing this video, I'm sorry, it's just because that's a massive amount of time spent on it, and I hope that you can just skip the sections where I'm faffing about and not making any progress. Okay, so now we have our folder here, and in that folder we have the bacpipe repository. Now we're going to create a virtual environment to make sure that we only have the packages installed in that project. So we're going to do cd bacpipe so now we're in that folder with the terminal, and we can check that by doing ls, then it'll list all the files that we can also see here. And now to create the virtual environment, I'm going to use UV. If you don't have UV, you can install it with pip install UV. There's also instructions on that in a lot of places, and ChatGPT will also be happy to help you with that. So we can just do UV venv, and then we'll specify that we want to use Python 3.11, and then we're going to call it env bacpipe. And now we have our environment installed, and we can just activate it. Now we're in our virtual environment. We can do uv pip list, and it'll show us that there's pretty much nothing in the environment right now. And so we're now going to install all the packages that we need. To do that, we're going to do uv pip install -r require PyProject. So there are also requirements files in here which you can use to install, but the big benefit of using the PyProject.toml file is that it knows what operating system you're on, and so especially for Windows users, it'll ignore all the packages that only work on Linux systems like CUDA and all of that. And so if you do that, then you don't have to think about these things at all. So UV is extremely fast, that's why I prefer to pip, and now it's installing all of the packages. And now that that's complete, we can uv pip list, and it'll show us all the packages that are installed in our repository. And now that was the hard part, and now we can start working with it. Now I'm gonna use VS Code for the next part, but you could also use, I don't know, PyCharm if you do the other editor, or you can also use just text editors to edit these files. But it makes your life a lot easier if you use VS Code. So by just typing code and then a dot, opens VS Code in that directory. And so now we are here. We have all the files that we need, and now run pipeline is pretty much the entry point. So if you do run pipeline, then it starts the whole program. So why don't we just start with that? And for that we need to, okay, so down here you would specify that we want to use the virtual environment that we've just created, .env bacpipe. If it doesn't know this immediately, then you just have to do enter interpreter path find, and then you just go into env bacpipe scripts and Python. In my case, this wasn't necessary because you already knew that. And if he does know that, then we can just, well, actually we just want to run it, so we can just do this guy. And that's just, I don't know, some Windows stuff, but the program is now running. And so what will happen on the first execution is that it'll download the weights for the BirdNet model. And the reason for that is that I think BirdNet is a good starting point. It kind of allows you to test the system, and it runs automatically and does like a first small evaluation based on test audio files that are included in the repository. And so it's more like a little testing thing to make sure your system does what it's supposed to do. And it might take a while because, like I said, it's downloading files, which we'll actually be able to see, hopefully. And that's in. So it'll create. There, you'll get this message. This seems to be your first call. Hi there, download model checkpoints from Hugging Face Hub for BirdNet, because let's face it, everyone needs a BirdNet, which I think is true. Even though there are a lot of models that are competing with BirdNet right now in regards to getting better performance, I still think BirdNet is a really good starting point, and they've put so much effort into creating their model, and they have a very convenient app for it and everything, and I think they're still they deserve a huge amount of acknowledgement for their contribution, and so I think it's always a good baseline to compare against. So it's currently now, so it's downloaded BirdNet, which you can see if you go in the folder. You'll see that we have this model checkpoints folder what it created, and it downloaded BirdNet, and it also actually downloaded this RCL FSPSAD, which is like a few-shot model. I'm just including it to kind of have another model that we can also test against. It's a very small model, so it's quick to download, and so. But like I said, we're still in the testing stage here. We're still making sure that everything just runs the way it should. And this folder here will get created automatically, and that's when all of this runs. Now it's starting to process files, so what it's doing is it's using files that we saved in this, just in the bacpipe depository. We have this tests folder, and inside tests folder we have test data and audio, and there are two folders with some audio files in there, and so BirdNet just produced embeddings for these audio files, and now it's going to do the same for the perch model, because the perch model is also in this little test app. If you just do bacpipe.play, it runs it with BirdNet and perch, just because the two of them are pretty established models. And perch doesn't actually require checkpoints to be downloaded, because it has a fancy Google API that allows you to, or that just does it in the background. It downloads all the things it needs, and so that's true for quite a few models actually. So maybe while that's running, I can go back to the website, and I can show you that all of the models that are included. So if you just go on model selection here, you can see all of the models that are currently supported in bacpipe. And I try to keep this list up to date with the state-of-the-art models, right? So the only one that's missing, I think the big one that's missing right now that's already released is Perch version 2. And hopefully by the time you're watching this video, it will be included. So this list will be changing and updated, and I'll try to make sure that all the new models, all of the ones that perform well, are always included. And you can actually also add your own models, which is, there's this add new model section, which explains how you would go about adding your own model if you have a model that you want to also compare against the others, right? And so BirdNet, we can see here, takes 48 kilohertz audio data. And so even if your data is 2 kilohertz or 15 or 225, it'll resample it to 448 to make sure that it's what the model expects. And then it takes these input segments of 3-second length and an embedding dimension of 1024. And Perch here uses 32 kilohertz. So we see they use different sampling rates, and they use 5 seconds, and they have a different embedding dimension. And if we go on this here, we can see more details on the models, and we'll see that for Perch, it tells you here checkpoint link. So the checkpoint link specifies the location if you need to download the weights for a model. And for the ones that don't need that, it says included, and you can see that's quite a few of them here, and that's because they are either models, either Google models, or they're Hugging Face models that have been pushed to Hugging Face, and then we can use Hugging Face's very convenient API to download them. And so all of that happens in the background. So as a starting point, if you don't want to go ahead and download specific models, you can always work with the ones that are included, and you'll be able to do all of everything with them. but it shouldn't take you much effort to, like, if you were to download them, we can actually go ahead and maybe just do an example for that. Let's download Nature Beats. And so this will take you directly to the download link, and then we can do download anyway. Now it's a massive file, right? This is a huge model, which I can explain in more detail later. And so it'll download this in the background, and while that's downloading, you can then, while that's downloading, we're going to look at the first results. So this is the dashboard that was automatically generated. So we can go back to see the execution here. Generating embeddings using purge bird, and so it finished that, and then it generates these UMAP embeddings. Now UMAP, for those of you who don't know, UMAP is a dimensionality reduction algorithm. So the thing is, because these dimensions of the embeddings are like, I don't know, 1024, 1280, something like that, obviously we can't really visualize data in 1024 dimensions, because 2 dimensions or 3 at most is what we can handle. And so we use some smart dimensionality reduction to kind of preserve the structure of the data, but look at it in 2 dimensions. And so everything you'll see is always reduced in a reduced dimensionality. And it then goes ahead and starts this this dashboard. Now, if it doesn't start automatically, you have this link here, and you can just alt-click that, and then it'll bring you to this website. But yeah, same thing. And so this is the dashboard that's created by default if you do this run play stuff. And it'll give you 3 tabs, and that's single model, 2 models, and all models. And the idea is pretty much for you to be able to evaluate a single model, but also to go into detail and look at and compare different models, right? So in a single model case, we can now we have this drop down of all the models that were used to generate embeddings. Now let's select Birch, for example, or BirdNet. Then we'll see that we have different embeddings. And now you can specify what you want to label it by. And you can label it by time of day, day of year, continuous time step, parent directory, or audio file name. Now, I know some of the formatting still needs work, but this was enough work as it is, and so that's why we're just going to have to bear with me. So the idea behind these things is that if you have a PAM data set, then all of the files will have timestamps, right? Like these files, for example. I mean, one of the beautiful things about passive acoustic monitoring datasets is that with each deployment we have a different naming convention for the time and day. But after a lot of fiddling, I kind of built something that I hope is stable to no matter what naming convention you used, it's able to extract the date time. And so if you have files that don't have datetime information, then you won't get this time of day, day of year, and continuous timestamp. But yeah, I mean, soundtrap data, audio mod data, they all have this datetime information somewhere on the file name, and so that's how you can use that. Now, the idea behind this is that let's say you have a massive deployment and you have a lot of different, doing your recordings over 4 months or something, and you want to see diurnal patterns, for example. And now all of these dots here, maybe I need to say that each dot corresponds to one audio context window, we call it in machine learning. And so a context window is pretty much like the window that is used to generate an embedding. So an embedding is just the model's representation of that input. And because BirdNet uses, we can go back to this website, we saw that BirdNet uses 3 seconds of audio and Perch uses 5 seconds of audio. Now, because of that, you're going to have different amounts of embeddings for the different models, right? So BirdNet, for example, so these are all 3 second audios, and then maybe we can see, it should be less embeddings, and so depending on the model, you'll get different amounts, but nonetheless, each embedding corresponds to a time within that audio file. And let's say, I don't know, if you have one audio file with an 8-hour recording or something, it'll generate this time of day because it'll extract the information from within the file. So each embedding will have like a segment, and that segment can then be calculated what time of day was recorded. Or for audio mod data, if you use a scheduler, for example, you'll have audio recordings where each recording corresponds to, I don't know, 30 seconds of audio or something like that. And so for that 30-second segment, then for Perch, for example, you'll get 6 embeddings because each context window is 5 seconds long. And so doesn't matter, no matter how you do it, you get this time date information. And so so if you're looking at diurnal patterns, for example, you can then see each of these points organizing according to, let's say, diurnal shifts. But maybe you also have all of your recordings in different folders. Like for me, for example, I have this. I have these folders. You can see them here. Few Shot and Urban Soundscape, and they're just. I mean, like I said, these are just test files. I'm gonna show you an example later that's more relevant, I think. But the idea is that we can sort by that, and so what we can see here, I think for Perch this becomes more clear. What we can see here is that all of these files are dark blue and all of these files are light blue. What that means is that Perch, like these two folders, because they're two different deployments, they have different noise backgrounds, right? And so first and foremost, the model is like, okay, there's a huge difference between all of these audio data. Even if we had the same birds vocalizing in some of these points here and some of these points here, the difference between the audio background is bigger. And for us machine learning like practitioners, this is actually quite important to see, because when you think that a model is really good at classifying this one species, if you only have that species from one location, it shows you, that model just understands that it's listening to this one location rather than to this one bird. And these kind of things are things that we're actually trying to like look in further, and there have been quite a few studies on this that came out recently, but the study that I initially built this tool for is also is about that, and you can it's down here, the citation. So clustering and novel class recognition, evaluating bioacoustic deep learning feature extractors. For those of you who aren't familiar with all this deep learning stuff, this might sound like a lot of stuff at once, but the idea is pretty much like, can we look at the outputs of the models in these embedding spaces in a way that allows us to understand what does the model actually think is similar versus what we think the model is like looking into. Okay, so these are the different label by categories. You can also do it by audio file name. If you have 5,000 audio files, this will get a bit messy, but this, like I said, I'm just trying to build one concept that kind of works for as many cases as possible. Now, we can also compare the models side by side. So we have BirdNet on the left here, and then we can have Perch on the right. Yeah, so this is Perch. So you can see if I do BirdNet, then we have the same. Or let's actually start with the same, because then we can compare the different labeling sections. So we can do time of day here, and let's do day of year here, and then we can see that all of the files, so these are exactly the same points, right? We're looking at the same embeddings, and we're just giving them a different color coding based on the labels that, or like in this case, the metadata that's associated with them. So if you have diurnal patterns, you can directly compare them with seasonal patterns here, for example, if you have deployments spanning several months. That's the idea behind that. And loads you can play around with, and you can also look at all models at once. So if you have, this is for 2 models, but if you use all 20, I think they're in there currently, then you'll get the same thing with 20 models. And that's the idea behind all of that. Now, I'm gonna go ahead and close this, and then we can go back and we can see if the checkpoint was downloaded in the meantime, and that will be downloaded in downloads. I'll maybe not show you all of that. And sorry, just bear with me. HLM audio. And documents. Okay, and then we have the file that we downloaded. We go into bacpipe, and then model checkpoints, and we paste that here, and then I'm gonna extract files. Yes. And now it's gonna extract them already to this folder, NatureLM Audio. Oh, okay, we actually only need one of that, so I'm gonna go ahead and copy this and put that here. Because the thing is, like, it has to be the model checkpoints, and then within that you have to have the things that you're looking for. So see, for BirdNet, for example, now this look different for different models. BirdNet is a TensorFlow model, that's why they have this format, and NatureLM Audio is a PyTorch model, that's why they have this format. And so now that we have the NatureLM Audio included, we're actually going to call it Nature Beats here. Oh, I think I have to rename this. So by the time you're watching this, you hopefully don't have to do this. But just make sure that the that the name the name of the checkpoint corresponds to the name of the model here. So here it's also called Nature Beats, I think. Yeah, Nature Beats, and so that name has to correspond to the one in the model checkpoint, and then just to make sure that he finds it. He being the bacpipe. And all right, so now that that's done, we are going to slightly modify the settings, and so we're going to go into bacpipe, and then we go into settings. And I can also show you the config file. So this is our audio dir, for example. Now we're using these standard test audio files, like I said. You would change this to the data that you want to use, but just for the rest of this example, I'm gonna add Nature Beats. Because we just downloaded that, and now we can include it, and we're actually also gonna include those two tasks, evaluation tasks, and I'm gonna explain that in a second. So now that that's done, we can go ahead and run our pipeline again. And so it's gonna look, bacpipe is always gonna check if you already have done if you already built the embeddings, right? So that's why if you look at the output here, we can see embeddings already exist using existing embeddings in blah, 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 blah. And so the place where those embeddings lie is specified in the very bottom of the settings file, and that's in the main results dir. So bacpipe results, and so because of that we can check if we go back to our main site. Bacpipe results, test data, and so the reason it's called test data is because that's the name of the data set that we're using. So the last segment here, please make sure not to use any spaces, because that always just makes everything harder. Use underscores. But if you have this, this last folder is always going to be the one that name is going to be used in the bacpipe results folder. And so if you want your results to be stored somewhere else, then you can also go into settings and modify this. Like you could also add a path, like if you do this, for example, then it will store it in the directory just above the one that we're in. But I'm not going to do that right now. But then in the config file, yeah, so that's the name that you can find the data in. And in here you will have, it'll create 3 folders. DIM reduced embeddings, embeddings, and evaluations. Now embeddings is the folder where the embeddings are stored, surprise, surprise. And for each of them, you will always have a timestamp. So when you created these embeddings, it won't be down to the second, just because that's usually unnecessary. So it's down to the minute. So we have 11th of September. That's when I'm recording this at 11:42, and we can see that. In here we have the audio data. And now again, the reason it's called audio is because in our test data... Okay, so we are back. I had a little camera stop because I was recording for too long. So what I was just showing you is the directory structure. And so if we look at the data that we're using right now, we can see in bacpipe test data, we have this. So this is our top level directory, right? Because here in config, we're specifying bacpipe test data. Then we can see inside the test data, we have this audio folder, and then we have this fuse shot and this urban soundscape folder, both with some recordings. And so because of that, we will then also have our embeddings created in the same directory structure. And so the embeddings are created based on this main results tier. And so if we go back, we can go to the main results. Here, that's the bacpipe results, test data. And then inside here we have 3 folders: evaluations, embeddings, dim-reduced embeddings. And inside of these folders, we will have the directory structure that's mimicking the structure of our audio files. And so that means that you have these NumPy files. So each of these files has the embeddings that correspond to the audio data that they sourced from. That's why they always have the name of the audio file that they come from, underscore, and then the model that was used. And so same amount of embedding files as we have our source files. And we also have this metadata file, and that contains information on where the audio data is coming from, where the embedding stuff is saved. So that's what we just saw. Embedding size, and then files, audio files, the file lengths of these audio files, and then also the number of embeddings created per file, which model we used, total embeddings, sample rate, and the length of the data set. Now you'll have that for each model that you use to process your data. And then you also have the dimensionality reduced embedding folder, and in here we have the UMAP embeddings. Now you can also, if you look here on the website, where are we? There. We can also see that we have three other dimensionality reduction algorithms that we can use if you want to. I'm not going to go into detail why. And then inside of each of these folders, it'll always have the name of the dimensionality reduction, then the name of the dataset you used, and the name of the model you used. And so let's say for BirdNet, for example, again, we have a metadata file, similar structure. This time it'll be about the number of embeddings from the dimensionality reduction. So embedding dimension is this is the original file, right? The 1024 coming from BirdNet, and now this tells you that we have so the original file had 22 embeddings, each with the size of 1024. So 1024 is always the same because that's just the embedding dimension of BirdNet, but this pretty much tells you how many embeddings per file were created, and then here it tells you again embeddings per file. And so for the dimensionality reduction algorithm, there's going to be a lot less files, so that's why you can also look at these JSON files, and you'll just see X and Y, just because we have 2 dimensions, and each of these numbers corresponds to the value that's from one embedding from that data set. And then down here you'll also have the timestamps, so each of the embeddings that it came from. So because we're not using the source files anymore in this naming convention, we have to make sure that there's some way that we can loop back to where did this embedding come from, and that's what this timestamp guy does for you. And then loads of other great stuff. And the third folder that we have is the evaluations folder, and the evaluations folder is where you evaluate. And so this is being created by default, and like the label by stuff that we had a second ago, that's all saved in there. And so so because of that, you're able to also look at these, load these files, right? Because the thing is, this so this file here, or this folder, you can pretty much copy, put on someone else's computer. If you run bacpipe, then they should be able to generate this dashboard without any processing having to happen, because it's already there. So it's pretty much like it saves you the exact status of that run that you did, and then you can then send that to other people if you want to look at it together, for example, and it doesn't require for them to do it again. So if you have like passive acoustic monitoring data of, I don't know, a year or something, and you want to process that with BirdNet, like it's going to take probably 3, 4, or 5 days or something, depending on your computer. And then obviously you don't want to do that every time you want to look at the data, and so that's why we're saving all of this, and that's why we have this search capability that bacpipe can look through the data and be like, ah, wait, we already did that, and then that's when it tells you like what's already been calculated, and that's why we save all of that. And so now, because we just activated the two evaluation tasks, clustering and classification, it also generates clustering and classification evaluations. Now, on top of that, we also used nature beats, and so because of that, our dashboard has grown, and we can now see that we have another model to choose from. So this is the nature beat stuff. Again, it divides really nicely, and we can see it divides by parent directory, so by deployment in this case. And but we now have a bit more stuff in here, and namely the species and k-means. Now let's start with k-means, because so that's a clustering, and so each of these little dots here corresponds to a cluster that the model created, right? Let's look at it for BirdNet because it has the most data. And you can see the clustering pretty much corresponds to like points that are close to each other in this embedding space, and based on that it pretty much tells you like, these all have a similarity. Now these don't have to represent meaningful things at all, but it's pretty much a way for you to check that. And the settings that are used for this clustering and classification stuff are defined in the settings. Surprise. And so you have this classification, clustering guy here. And so inside the clustering settings, you have, you can also evaluate with the silhouette score. And then for cluster configs, it's pretty much like the configurations for the clusterings. So in this case, we're running we're actually just running one, but we can run two clusterings, and so for that we would need to set this guy to true. I think then you need to install the HBD scan clustering, but more on that later. So we have the clustering configs, and for our clustering that we're using, we have this, we just set it to true. That means it runs it. But if, like, let's say you have 4 different setups that you usually use, then you could also just do this, name this clustering 2, clustering 3, all of these, and I'm like, don't want to run this one really, don't want to run this one, and I'm gonna want to run this one, and I'm gonna want to use the clustering number of clusters. I'm gonna bump that up to, or I'm gonna lower that to 3 or something. Like, the idea is pretty much that, like, if you have 5 different species, then try using 5 clusters and see if he's able to differentiate between these species by clusters, right? Okay, but if you're not interested in clustering, then that's also fine. We can also, it's just another way to kind of like visualize the differences in the data. And another thing that this offers you is classification evaluation. And so we're using 2 classification types, and that's KNN and linear classification. And so you can also see the results here. I think I'm going to do a Q&A session on this later on if there's a lot of interest, because there's a lot to delve into right now, and I don't know if anyone's interested in it as much as I am. And so these results are completely ridiculous. It's just because we have 6 files, and like doing this analysis for 6 files is pretty much just pointless. But it's more about like a proof of concept that this all works. And so so it generates you these classification scores, and then we can look at KNN or linear classification, and that's all great. And the last one, that's probably the most interesting one, is the species category. And so the species category comes from the fact that we are feeding the model annotated file. And so if we go back to our bacpipe stuff, inside the test files, where are we? Test data. we have this annotation.csv file. And so this annotation.csv file, maybe we can open that with something that looks a little nicer. In this annotation.csv file, we have 4 different columns, and the columns are, oh no, we don't want that. The columns are audio file name, start, end, and then you can add different label categories. And so it's important that it's always label colon and then whatever you want to look at, right? So we could change species to call type or something. And then if we do call type, for example, or we have another column here, and one is species and one is call type, like if we do this, for example, then let's just test this because I think it's good if we show things. Then we can run the whole thing again. And you're always just executing run pipeline, by the way. So run bacpipe.play is always what you execute, and you're just changing the settings and configuration files. And so I actually modified the annotations file a bit more to make sure that the label call type and the label species aren't identical, but that we have the call type A and B, let's say. I mean, this is just arbitrary, right? We're throwing some B's and A's in there, but the main purpose of this is just to show that you can look at your embeddings and color code them in different ways. So I'm going to save this and then close this, and now we're going to go back and run pipeline. Run pipeline is always the entry point, right? Like you pretty much just end up running this file, and then you modify the settings and the configs file based on what you need to change. And you'll see a lot happening here, and it's happening very quickly. And the reason for that is that we already generated the embeddings, so you'll always get these messages here in between. Embeddings already exist. And the same is for the UMAP embeddings. Embeddings already exist. And this saves you all of the computations, which is the bulk of the time. So pretty much what the bacpipe only has to do is load the files and display them, and that's a lot quicker. And that's why that's what we're doing. And so if we now look at our dashboard again, we can see that we have the 3 models here. And now we have a call type here. And so we can look at call type and we can look at species. And so these colors will correspond to the different columns in your annotation file. And now this little noise guy is also there because let's say in your annotations file we haven't annotated every segment of the entire data set, of course, like we annotated a small portion, for example. And then you can just remove noise and it'll get rid of all of the points that don't correspond to annotations. And so if you do that for call types, if we remove noise, or if we leave the noise in, then we have noise there, remove noise, and you can see the little orange dots are going to disappear. And so this is quite helpful if you have a massive data set. And so let's see, we can compare 2 models, and we can, again, let's compare nature beats to perch, and let's see how well they do by call type differentiation. And we can then see, and we're gonna remove noise for both of them, and then we can see like, okay, they cluster it in these ways. As I say, like, I mean, this is arbitrary data. I'm sure you have way more interesting data lying around on your hard drives, and yeah, go ahead and explore. And again, this is the overview. Now we also have nature beats here because we added another model. With every model you add, it'll add to these displays, and then for all of them we can differentiate by call type, we can differentiate by species, and all of these things. And I think for BirdNet, let's see if we no, okay, that'll be a separate video. Or actually maybe I can do it now. So the thing is that we can also use classifiers that are already included in the models. And now a lot of models don't have that, but BirdNet and Perch, for example, they do. So I'm going to go ahead and cancel this, and then if we look at the got some error here, I'm going to check it out later. If we look at the settings file and we look at the run pretrained classifier true setting, then this will allow us to also visualize the data based on the classifications from the models that are included. Okay, so I'm actually going to run this with NatureBeats first, just to kind of like show you what happens, and then after that we can look at it without NatureBeats. And so so all the classification stuff is done, and so we now have this added category, default classifier. The default classifier corresponds to the classifier that is shipped with the model. So in case of BirdNet and Perch, they are included. And if you go on NatureBeats, you end up with a big white figure because we don't have any classifier for NatureBeats. If you also go on all models, and if you then compare by default classifier, it won't do anything, and it'll also fail. Like if you look here, you will have this error message. So the easiest way to avoid this is just to go into the config file and make sure that all the models that are actually activated are the ones that also have the default classifier. So now if I run this again, we should be able to see that if we do all models, we can now compare by default classifier. And so all these classes will correspond to the classes that those model classifiers already know. Now, important, you need to set this flag in settings, run pretrained classifier to true before you execute your embedding generation. Once a generation of the embedding is done, you're not able to add that afterwards. That's just because the way I built that. Maybe that'll be fixed in a future version. But for now, make sure that you activate that afterwards, that you activate that before to make sure that the classifiers are already used during chaining. Now, the reason that's default false is because it can increase the computational speed. Most models, it doesn't take long to also do their classification step, but for some models like Perch, for example, they have a massive classification head because they have this hierarchical classifier and blah, blah, blah. It's all like great what it can do, but this bacpipe is really about generating embeddings, and so that's why the focus is embeddings, and that's why by default this is false. But yeah, if you do a massive run, make sure to set that to true. The classifier threshold is important because, so BirdNet, for example, knows 9,500 classes, I think the version that's supported here, 2.4, and now most of those classes are definitely going to be close to zero, right? So we don't want our results being cluttered with all of these massive amounts of arrays that are pretty much all zero, because for most classes we don't have any relevant species, and so you can set a classifier threshold. Now 0.3 is still quite low, too low I think, to get meaningful results, but the idea is that you have all the species that the model thinks are likely to be in there, and at the same time you're not cluttering it with like everything, right? So you can still do a lot of post-processing analysis here, looking at species that BirdNet almost thought were in there or something like that, but it's not as messy as if you would have the whole thing. And so that's why in the dashboard you'll also see like all these species. Now the reason that's a color bar is just because it's like, I think it's like, I don't know, 500 species, no, in this case maybe it's like 50 species or something, and if I would have like little label dots with a color, then it would just be like you wouldn't be able to see anything. So I'm showing a few species here. Each species corresponds to one color, that's why we have this color bar kind of layout, and but yeah, you can see like this, for example, is all one species, so maybe that's all blackbirds or something, and so it's one color, doesn't show here, but that's just the color bar legend kind of thing. And if we look at the data that's being generated for the default classifiers, we can see in the evaluations, BirdNet classification, we now have this original classifier outputs, and if we go in that, again, it mimics the directory structure, and for each audio file that we use, we have now a corresponding JSON file, and for that corresponding JSON file, it'll tell you the time bins where it found these species active. So in this case, there's only one species that's active, that's a common cuckoo, and we have 3 predictions, each with a value of 0.5 something, and this is the locations of that. And now this is maybe not that easily readable for a human, but we're storing it because we can then use that to combine it with another repository that I built called ACODET, but there's going to be a separate video for that. But what you also get here is this default classifier annotations file, and that is a bit more interesting to look at, because what this tells you is it's in the same format as the other ones, and it tells you for each embedding that was created, it tells you the species that was most dominant there, right? So you can see the style is exactly the same as the annotations file, so technically we could use this now, feed it into the model as annotations, and then use it to evaluate nonlinear and KNN classification and stuff. Of course, it's important this isn't ground truth. These are model created. Predictions, but it's still. I mean, BirdNet is a model that's trained on a lot of species, so it won't be completely ridiculous. And the species also all make sense because this was here in the Netherlands. And so, but it only includes embeddings with where the highest prediction that's shown here also exceeds that threshold value, as I said earlier. So if you have some gaps in the data, then that'll be the reason for that. And yeah, so that's that annotations file. Hopefully that is meaningful to some of you. And what's also, I'll stop that there. And on another note, if you activate the classification, as we said earlier, then what happens is that it generates for you a linear classifier that's also being saved, and that's this file here. And so the linear classifier that is being saved, I think it's still active in the thing. Yeah. So we still have the evaluation turned on with our classification and clustering. And so if we go on the linear classifier here, we can see that, let's just look at it for a single model. Let's look at it for BirdNet. We're going on the linear classifier here, and then we can see down here the performance. As I said, again, like this is completely overfit, right? That's just because we have so little data that we're actually working with, and the annotations that I used, I mean, as you saw, that's also a bit, like I just created that annotations file with the call types and stuff. It's it doesn't really mean that the annotations are of good quality. But what you can do is, once you do the linear classification, you also get this, it saves you the linear classifier file. And so these two files are then important because you can then also export them to, or you can use them in this other repository that I built, bacpipe. There's going to be a separate video for that. You can use that to include it, and then you can use it to actually generate species predictions. Even like, let's say you have a massive PAM data set and you're interested in the frogs there. Now, there's no good model out there that's trained on frogs yet, but then you have a small data set of frogs, you annotate that, you do linear classification, then you have a linear classifier that knows to now distinguish frogs, and so that now allows you to use this big pre-trained model with a small linear classifier that you built on top of it, import that into ACODET, and then you can get species generation for your frog data set, even though you never had to like completely train a model from ground truth. And that is the power of these pre-trained models, and that maybe should come in the beginning of the video, because I think the importance of pre-trained models is that they're trained on so much data that they learn to give a good characterization of acoustic sounds, right, of species vocalizations. And so by using linear classifiers, you're pretty much just tweaking the last little bit and just telling them like, okay, you're already good at like differentiating between birds. Now here are frogs, and this is one frog, this is one frog, and this is one frog, and now learn to separate them. And then takes you, I don't know, a minute or something to train that linear classifier, and now it's able to differentiate between these three frogs. And so what you can now do is you can use that massive pre-trained model. Ooh, someone else did the work there. Thank you to them. And then you take that pre-trained model, you put it into ACODET, for example, then you put the linear classifier on top of it, and boom, you now have a working model that allows you to tackle your large PAM data set. Okay, but that was the quick rundown of bacpipe. Now maybe for a more interesting example, I'm going to show you how you could work with data sets that were already generated with embeddings, and how you can import them and then use them. Okay, and all right. Okay, so now we're gonna look at a more interesting scenario, and that's an actually interesting bioacoustics data set, and that's the AnuraSet, or AnuraSet actually. I just misspelled it, and now because I already generated it, I'm gonna have to go with my typo, so sorry for that. Sorry, Juan. So this is the AnuraSet. We have 4 different deployment sites, and we have a lot of data in each of these sites. And so, and we also have annotations for that. And so I generated embeddings for that data set, and that's here. And so I generated embeddings using bird, MAE, and nature beats. So first of all, we need to download the bird MAE. No, actually we don't, because we already generated the embeddings. And so that's also nice. If you share it with someone else, they don't need to download the checkpoints or anything, as long as you have the embeddings. Bacpipe should be able to work with everything you need. And so it's still gonna need you to input the audio dir, just because it's like for where it looks for the files. And so I'm gonna go to this here. I'm gonna select this path, put it in here, and then yeah, that should hopefully not be a problem. And so we're gonna get rid of those 2, and we want nature beats and bird MAE, and blah blah blah, clustering classification. Let's keep those off for now. And why is he complaining? I think it's because it's so let's see if he likes that. I think for Windows paths you might have to do that, because he doesn't like the backslashes. Or maybe what's easier, sorry if you're on Windows, turn them into backslashes. That's just because YAML is funny like that. And then yeah. Okay, so now that we've done that, we have our files and everything. We don't really need to specify anything different here. Now the important part is just that it knows where to find the embeddings, right? So right now it's looking in bacpipe results, and even though this other guy is also called bacpipe results, it's in a different location. And so because of that, we're just going to give him this path, just to kind of like, or maybe it's easier, I think, if we just copy this and put it in the right location. So we have bacpipe results here, so if we copy it in here, then it'll add AnuraSet in here, and then we'll have the code, we have the embeddings in the right place. He'll know where to find them. And so let's go ahead and run that, and we can actually, let's also activate the clustering and classification, because, so the thing is, he looks for the annotations file either in the root directory where the sound files are. No annotations file here. It's actually just above here, but we're just going to stick with that, just because there's like some, I don't know, other crap. I want to make sure he doesn't take any files that he shouldn't. And we do have the file here, so because of that, he should also check this location. But if you don't have the annotations file in this directory or this directory, then it'll be a problem. Okay, and now that we have done all that, we let's overwrite the click overwrite true, because the thing is, we have the embeddings, but we don't have any evaluations, and we don't have any dimensionality reduced embeddings, which we all need. And so let's execute this and see if that works or not. Okay, so I just realized that for Windows users, it's important that you don't use any quotations here. Because this is not a Python file, it's a YAML file, this is already interpreted as a string anyway, and if you put quotations on it, then it just messes the whole thing up, because then you get these backwards slashes, and that just causes problems. So no quotations for Windows, please. We want to keep these clustering classification on. Now we make sure we only have nature beats and bird MAE, and let's actually, let's overwrite the stuff because we don't have all of these other features that we need. And just because we want to try that as well, we are going to go into we're going to find the embeddings again, and I created this results folder, and in here is the AnuraSet, and that's where so I'm actually going to delete these because we're doing a tutorial and we want to start from scratch. So these are where the results are. Let's say you did the results on your server or something, and then you're bringing them to your computer. But let's say you only have the embeddings for some reason, and then the embeddings and the annotations file. And so we can just take this path and we can go to the settings file, and then we replace the main results directory with that path. Again, no quotes for Windows, make sure. Okay, so now that we've specified that, we've specified the configuration and stuff, then we can run our pipeline again. And so in this terminal window, you should hopefully see that he finds the embeddings, and no, he doesn't. And I think the reason is because I added the AnuraSet here in the end. So we want the main results directory, right? So the top level directory. AnuraSet is already a data set, so that should already be within the main results directory. Okay, so that's why that caused a problem. So now you can see he created a new AnuraSet folder with these stuff, but that's all empty, pretty much empty. Yeah. So we're gonna go ahead and delete that again. And now that we have the correct path, we can go back to run pipeline, execute. And now hopefully he should find the embeddings. Yep, that's what we want to see. So embeddings already exist using existing in blah, 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 blah. Audio files are no longer where they used to be during the previous run. And the reason he knows that is because as we've seen before in this metadata.yaml file, we save the location of all the files. Now, it's not a big problem right now. It's just for some, like if you, I don't think there's actually any scenario. I think that's just for some of the stuff I did. It's just letting you know that things are in a different place. He's now generating the dimensionality reduction because that wasn't there for the original files. Now, you saw how quickly that worked originally with that test data, but that was 7 files. Now we have 1,612 files. So obviously the dimensionality reduction is going to take a lot longer. The embedding, I think, took me, actually, I think the embedding took me maybe like 2, 3, 4 hours, something like that. And I think I did that on a server that has a GPU available. So by the way, if you have a server with GPU available, you can just go to the settings, change the device to CUDA, C-U-D-A, as it also says here. And if you do that, then he will use your CUDA device, and that will speed up the processing of the PyTorch models by quite a lot. Global batch size, this number is also important. If your computer has small memory or massive memory, then go ahead and modify that to your needs. But these things are, you can also just email and then ask what these things are if I haven't explained anything very well. Okay, now he's generating embeddings for the UMAP embeddings for bird MAE. We can have a look in the meantime and see if, okay, so we have these folders now, and we see dimensionality reduced embeddings for nature beats, bird MAE, and we also have the evaluations here now. So he did everything that we wanted him to do, and so while we wait on that to finish, I can just maybe point out other things, maybe just for the structure of the repository. The way it's structured is that we have this main bacpipe folder, and in there we have the embedding generation pipelines, and in the embedding generation pipelines we have feature extractors, and these are all of the Python modules that you would use to generate the embeddings, right? And so they're for each model pretty much like how to run the model, everything. And so for all the provided models, this is already done. If you would want to add a model, then you can orient yourself based on the ones that were done here. Okay, and now we have our everything in place. We turned off clustering classification. Actually, why don't we just keep them on? I know, a bit of back and forth, but there's no reason not to. And then we can go ahead and start this thing. And now we should see, yeah, he finds all the embeddings just like we want him to, and now he's generating the classification. And now he found 30 unique labels. He's training our classifiers, that's what this is. So he's doing 10 epochs, that's all specified in the settings. And linear classification, where are you? Clustering classification, there. Linear classification, we're doing 10 epochs, batch size 64, learning rate 0.001. Play with these parameters. I mean, these are like the defaults, they're fine, but yeah, you can go ahead and play around with them. And then you'll get slightly different results and slightly different classifiers. The classifiers will be overwritten, so that's just something to keep in mind. So, okay, we generated our classification, everything works the way what we hoped it to, and now we can see our embedding space. Now, these are the embeddings for all of those 1,612 files. Maybe just to show you, impress you with the stats. We can look at the metadata file and we can see that we have, so originally when I computed the files, they were on my other computer, and that's why he's complaining that they're not in the same place anymore, because this path doesn't match with the one now. All of the audio files, they're all about like 60 seconds long, and we can see we have a total dataset length of 96,000 seconds, so that's what 300 minutes, so 5 hours, round about that. And so yeah, this is more model specific stuff, but so 19,423 total embeddings. So that means we're looking at 19,423 points here, and each of these points represents, for the nature beats model, that's then 5 seconds of audio, so just samples divided by sample rate, 5 seconds of audio. And we can look at bird MAE, I think it's also 5 seconds, and we can see that they're slightly differently structured. And now if we scroll down, this clustering is actually more interesting to look at now, and now we can do this. We can have our bird net, let's do bird MAE on both sides, and we can compare the time of day with the k-means clustering. And so it'll take a second to load. Okay, and now when we look at the embeddings, we can look at the k-means cluster, and so the clustering will now be a bit more meaningful. The number of clusters corresponds to the number of species that are in the annotations file. So that technically, if you did a fabulous job, every species would have one cluster. Now, as you can see, it's obviously a lot more messy than that. But let's look at the two models side by side. Let's look at bird MAE, and then we can compare, okay, these are the time of day color codings, and these are the k-means clusters. And we can kind of, we're not looking at the same model. And we can compare here, like, if certain clusters are more likely to correspond to one time of day, or if we compare it to species. And this is also important, again, we have a lot of noise, so these are all the segments that aren't annotated, so let's get rid of the noise, and we can also do that for the clustered ones. So now if we look at the, now if we compare the k-means cluster to the species cluster, we can see if he did a good job. So we can see all of these very dark blue ones here, that looks like it's one species, and we can see that he clustered it as 4 different clusters. And so, yeah, I mean, this is a very large data set, and there's probably a lot more that you could do, more digging that you could do in here. But those are kind of the results that we can then see in this clustering overview, right? So this tells us how well does a k-means cluster with species. And so we can see, we can pretty much see how well they're doing. So what we're looking for here is how much do the k-means clusters overlap with the species clusters. But if we look at our classification stuff, then we can also, let's look at the same. So let's do one model to nature beats. Now we can see for each species of frogs how well the linear classifier that was trained, or actually in this case k and n, now it's a linear classifier, and for nature beats, we can see how well the linear classifier, how good of a job it did at classifying all of these species. And so we divided the species into like a train and test set, and then we trained it on the train set, and then we see how well it does in the test set. All of that happens under the hood automatically. But yeah, you can dive into code if that's your thing, or you can send me an email and ask if you have more questions about that. And we can do the all models comparison. So now again we can do, let's look at the time of day, for example. So this would be diurnal patterns. Let's get rid of all the noise, and then we have all the annotated segments. Now we can also see that most of the annotations were maybe happening around certain times of day or something, but that could also be just down to the times that the data was collected. So I'm not going to go into much detail in this analysis now. There's the conference paper that this is also mentioned on the repository page is there's a lot of stuff collected there because we did like a clustering classification analysis also on this AnuraSet data set, pretty much with the approach that we're taking here. And so you can see how well the different models do at clustering versus classification. And this is quite interesting because now we can, it's a bit annoying that it puts it so much on the right. Now we can look at the different deployment sites, right? Because AnuraSet was collected in 4 different sites. And if we now color code by the different deployment sites, we can see that, for example, this INCT4 seems to not really have one coherent noise environment that dominates the model's characteristic association, if you would call it like that, but it's more scattered. But if you look at the light blue one, which is the INCT 2955, you can see that it's a more dense cluster. So if that's down to the fact that there are certain species that are occurring all the time, especially with in some of these locations where they did their recordings, this is tropical rainforest, you have some species vocalizations in the background that are just continuous, right? Continuous vocalizations of some species, then that'll be a very prominent feature in the sound. And so the model is likely to have a hard time, let's say, filtering that out and looking at the target species that you're interested here. If we put the noise back in, we can see this is even more pronounced, right? So now we have the entire unlabeled data set, and we can color code it by the different deployment locations. And so we have the dark blue, we have this orangey part, and blue part, red part, and it really shows us how the models kind of structure these sounds. Of course, with these huge data sets, it's then also a problem because now it's so much data that you're looking at that it's a bit tricky to actually gather some patterns from it. And so because of that, this is my lead on to the other repository. There is a repository that I built called ACODET, which is called or stands for acoustic detection, and it's you can find it here, and it's pretty much aimed at giving you a graphical interface to explore the predictions that were created by models. Now I'm going to make a new video on that, but just so you know, if you run the classification algorithm that's included here, so if you just set the config classification to true, then it will create your classifier, and that's going to be saved in the evaluations classification folder, and that's these 2 files here, and they can then be used. So regardless of the ACODET stuff, you can use those 2 files and just take the feature extractor, which is publicly available, add that linear classifier on top of it, and then you have a full functioning model, which would now probably do a decent job at classifying frog sounds, because it was trained on a lot of data, all of the data that the people from the AnuraSet annotated. So yeah, I just think this is a pretty cool capability of these models, and that's what this whole project is about. And yeah, I hope I didn't leave anything out. If I did, please feel free to reach out to me, raise an issue if there's any problems. I'm sure there's going to be issues. This is like, I mean, each data set has its own kind of like quirks and problems, and so because of that, it's very likely that there's going to be shortcomings. If you're a coder yourself, please feel free to contribute. This project is massive, and so any help would be really appreciated. I'm just trying to keep the repository as clean as possible in terms of like no more dependencies. Like I really don't want to add the number of files that are like being used in the repository, so I have like some kind of like manifest ideas of this repository, but when it comes to adding features, making things more stable, I know that there's bugs in there, so if people run into bugs, like if you know how to fix it, then yeah, it would be really a great help if you would do a pull request. Please make sure to always do the PI tests and make sure that everything runs on your machine before you're finishing your pull request, just so we make sure that everything that's going to be pushed is also stable. But yeah, or if you have any other feature requests, dashboard visualization, suggestions, anything like that, please let me know. And also I created a newsletter, and if there is a demand for QA sessions or something, then I'd be happy to do that. And yeah, the link's on there, so feel free to subscribe. And I think if there's gonna be 20 or 30 people signing up for that, then I'm gonna schedule a Q&A session, and then we can have an interactive chat if there are any questions that this video doesn't answer. If you've watched all this time, respect to you, and thank you very much for being so interested. Yeah, sorry for the style of the video that's a bit like jumpy and everything. It's just because I'm like, yeah, not a professional YouTuber, and I'm just doing this as a side project, and yeah, hope you bear with me. And stay tuned, I'm gonna release another video probably shortly that's gonna be on how to use ACODET to have a graphical user interface to actually use those linear classifiers that we train, put them on top of the feature extractor, and then get like heat maps of species activity and all these kind of things. Alrighty, thank you very much, and take care. Bye-bye.